Yes.
Good evening, everyone, and wish you a 2021. All of you. On this auspicious day, our college has organized international webinar on large deviations for random graphs. We feel very happy and take pride in the presence of the renowned speaker, Professor Sourav Chatterjee, Professor of Mathematics and Statistics, Stanford University, who will enrich us with his wisdom and knowledge. Our Principal Maharaj for a short welcome address.
So, respected Professor Sourav Chatterjee, the professor of Stanford University, USA. He is our today speaker, and my dear colleagues and my dear students, those are present in this platform and other YouTube and other platforms. So it is a very good evening to everybody, because we are happy that in our midst Professor Sourav Chatterjee, renowned mathematician, I can tell, because recently all you have, I think, heard and also go through the this media and newspaper that recently this 2020 he has got the prestigious Infosys Award 2020. So this, and all you have know that Infosys award, it is a very, very prestigious award. I can say it is a very good international award, I can say, because it actually gives a good pure gold medal to the winners, and also they can get the 1 lakhs USD dollar. So you can understand this gravity of this international this award, Infosys award. And from mathematical science, actually 6 division Infosys award, actually every year they awarded the prospective scientist in the 6th field, and among these 6 fields, this mathematical science is one. And this year, this Professor Sourav Chatterjee got this Infosys award. So, so I, on behalf of the college and behalf of all you and faculty members, I extend my heartiest congratulations to Professor Sourav Chatterjee for his achievement, for his sincerity, and for his dedication. And I tell specifically the students that he is a very, very honest and sincere mathematician. His approach and everything so sincere that I think from his deliberation, if you can learn something about mathematics, that is no problem, but you can try to learn his sincerity. Because the last few days through mails and also last day, this for demo purpose, I interact with him, and I just come across such a sincere scientist. So I tell the students, please actually enjoy his talk with your utmost sincerity, and after this talk you interact with him, and I answer, give some, you ask some question, and through this you also enrich yourself. And with these few words, I extend my heartiest welcome, and also our all regards to Professor Sourav Chatterjee for his achievement. And I also pray to Thakurma Swamiji for his future prospect and future actually this well-being. And with these few words, I once again welcome him, and also welcome all of you those are present in this different platform in this webinar. So thanks all of you in this beautiful evening. Thank you.
Thank you, Maharaj. Before start this, I would like to tell some words introducing Professor. He was born at Calcutta, but at present he is permanent resident in the USA. He had passed BStat and MStat from and received PhD degree in statistics from Stanford University on 2000. And then from September 2013, he became a professor of math at Stanford University and successively institution. He got many recognizable prestigious awards since 2007, and in last year, 2020, he received the Infosys Award. He published many books and many useful journals. So I would like to request him to proceed for his lecture.
Okay, thank you for the very kind introduction and the invitation. I could have spoken in Bangla, but maybe there are some students who don't understand Bangla, or and also this is a technical, mathematical talk. That's what it's going to be. I'll speak in English, but in the question answer session, feel free to just ask questions in Bangla. Okay, so that's fine. Okay, so this is a topic: large deviations for random graphs. It's going to be a technical talk. It may be a little difficult for some of you. So Shamiji told me that there'll be both BSc and MSc students. It may be a little difficult for BSc students, but just try to follow along what and ask questions later. So so let's see. Okay, so let's start with what is large deviations. Many of you may have heard the name, the theory of large deviations. It's a part of probability theory, and also I'll assume a little bit of knowledge in probability, just basic. What is a random variable? Probabilities and expectations, that kind of thing. So I'll assume that sort of knowledge. So the theory of large deviations aims to study two things: the probabilities of rare events. So rare events do happen. So they are rare events, but occasionally they do happen. What happened last year, what in the coronavirus pandemic was a rare event. Nobody could have thought that would happen, but it happened. So rare events happen, and what it also tries to understand is the conditional distribution of random variables given that some rare event has occurred. That is, what does the world look like if some rare event happens? So that is also not clear. So the usual state of the world completely changes when a rare event happens. So then we want to understand a priori. We want to understand what's going to happen if some rare event takes place. Okay. So for example, part A would be what is the chance that you will win the lottery, and part B is how is your life going to change if you win the lottery. So these are both random things, and these are both interesting questions. The second question is often more interesting. That is, what is going to happen if some rare event happens? So you don't often care about the exact probability, but suppose it happens, then what's going to happen? But we usually need to answer the first question first to be able to answer how to approach the second. Okay, so there are many reasons for that, but that's a basic thing, that we need to first understand the probabilities of rare events, how rare it is going to be to be able to answer the second question. Okay. All right. And also, in the talk, just stop me anytime. I would, if you can unmute yourself and ask questions, that's fine. That is also good. Okay, so a simple example: you toss a fair coin n times, where n is a large number. So you take a fair coin, equal probability of heads or tails, and you toss it n times. So under normal circumstances, what you expect is that you expect to get approximately n over 2 heads. That's the law of large numbers. So if you toss it 1,000 times, you expect to get 100 heads. Okay, and you also expect to get roughly n over 4 pairs of consecutive heads. So if you toss a coin 1,000 times, and you ask what's the number of times that you get 2 heads in a row, okay? Roughly you would expect n over 4 of such things. So if you toss it 1,000 times, around 250 occurrences of that, 2 heads in a row. Okay. So suppose now that the following rare event occurs, you get approximately 2n over 3 heads. So like you toss a coin 1,000 times and you get 666, something around that, maybe 650 to 670 heads, something like that. Okay. So that's a very rare occurrence. That doesn't usually happen. What the theory of large deviations will tell you is that you can approximately compute this probability. The probability of this rare event is approximately this e to the minus n times log of 2 to the 5 over 3 divided by 3. Some slightly complicated number like this. Okay. So moreover, so that's the part A of the thing, that is trying to compute the probability of the rare event. So I'll briefly tell you how this is computed. Okay. And the second question, what happens if this rare event takes place? So suppose this rare event takes place, okay? Then you can say that instead of n over 4 pairs of consecutive heads, if you can count the number of consecutive heads, it's going to be roughly like 4n over 9. Okay, so this will change. So as soon as you know that the number of heads is much bigger than what it usually is supposed to be, you can conclude from that very occurrence of that event. If somebody tells you this has happened, you can say that, well, it's very likely that there are sort of like 4n over 9 pairs of consecutive heads instead of the n over 4. Okay, so this kind of conclusion you can draw using the theory of large deviations. That's what the theory of large deviations is about, and this theory was pioneered, and large part of it was developed by Professor Srinivasa Varadhan, so he's our fellow countryman. So he did that in the 1960s and 70s and 80s, for which he got the Abel Prize. So this was the theory of large deviations has a very sort of Indian touch to it, and so that's one thing that many of you may not know that. And it's extremely widely used, this kind of thing. So in all kinds of situations that, in engineering, it's widely used in engineering, in the physical sciences. They all want to know probabilities of rare events and what will happen if a rare event happens, because rare events happen all the time. I mean, so some event may be rare, but if you have many possible, thousands of rare events that can happen, then one of them may just happen, that kind of thing. So how is this estimate obtained? Okay, so here I'll assume some knowledge of or basic of things about probability. So suppose you have independent random variables x1 to xn, such that the probability of xi is being 0 is equal to the probability of xi being 1 with equal to a half for each I. So xi is 0 or 1 with equal probability. Then the number of heads in n tosses of a fair coin has the same distribution as the sum of these random variables. Okay, x1 plus up to xn. So this is Sn is the number of this is how you mathematically formulate the number of heads in n tosses of a fair coin as the sum of independent random variables. So these many of you may know these are Bernoulli random variables with probability half. Okay? And so this is how you get an upper bound. So the chance that the number is bigger than 2n over 3, Sn is bigger than 2n over 3, what you do is you take some theta positive, and it's the same event as saying that e to the theta Sn is bigger than e to the theta 2 theta over 3. Okay? And then you apply what's called Markov's inequality, the chance that a non-negative random variable is bigger than some threshold. So if you have a non-negative random variable y, the chance that it's bigger than some number a is bounded above by expected value of y divided by a. So that's Markov's inequality, or sometimes called Chebyshev's inequality, although Chebyshev's inequality is a second moment version of that. It's a little different. So you just apply this inequality, and you get this, okay? This bound. And then Sn is the sum of x1 to xn, so e to the theta Sn is the product of e to the theta xi. Okay, so it's the expectation of this product divided by e to the 2 theta n over 3. So expectation of a product now becomes product of expectations. Again, I suppose many of you, if you have taken a course in probability, you know this, that the product of independent random variables, the expectation is the product of expectation, so you get this. And then this is easily computable. So you can compute the expectation of this e to the theta xi, and you get this number, and then you get this. And then what you do is you get this bound, and then you optimize over theta. So you try to make this as small as possible by varying theta. So that's a calculus exercise. Okay. So you do this calculus, and you get an upper bound. And this gives you the upper bound that I showed. Okay. So this is how the upper bound is obtained. Lower bound involves a different idea. So this is something different that we do. So this gives you a slight flavor of how large deviations are done. So in this very simple example. Okay, so this example has this built-in linearity which allows us to compute this explicitly to compute this expectation e to the theta Sn. And so large deviations theory, what it does is that it generalizes this idea, and it has this collection of powerful tools to deal with linear functionals of independent random variables or more abstract random objects. So this is what large deviations theory is about, but there are no general tools for nonlinear functionals. So this is what I'm going to talk about. And then let's look at a simple example. Okay, so this networks. So it's a huge industry now to understand real world networks. So there are all kinds of networks, social networks, biological networks, gene networks, all kinds of things. And rare events on networks are often this nonlinear in nature. So I'll give you a very simple example of rare events on networks. So consider the following simple model. Okay. There are n individuals. Any two are friends with probability p and not friends with probability 1 minus p. And friendships form independently. So you are considering a hypothetical social network, like in Facebook, and you have this n individuals, and any two become friends with probability p and not friends with probability 1 minus p, and friendships are independent, so they all form independently. So what you get is called what's called a random graph. So this is called the Erdős-Srény random graph. Erdős-Srény, this is called a GNP model. And it's not a realistic model, but it's a first step towards understanding real networks. So there are many features of real networks that you can sort of understand here, and then move to more realistic models. Okay. Now, in graph theoretic terminology, an individual is called a vertex, and a friendship between two individuals is called an edge. That's the graph theoretic terms that we are going to use. Okay. So, if anyone has any questions, you can ask now, but otherwise I'll go on. Okay, so let me describe a rare event in this model. So you have this random graph model where you have n individuals, and any two are friends with probability p and not friends with probability 1 minus p. And you can compute that the expected number of triangles in this graph, in this random graph, is exactly equal to this: n times n minus 1 times n minus 2 times p cubed over 6. So I'll not go through that computation. So this is something that you can do, and it's it's sufficient. Undergraduate probability is enough to do this computation, so it's not a hard computation. So the large deviation question is: what is the probability that there are k triangles where k is some number much bigger than the expected value? So if you take this expected number of triangles in this graph and look at some number which is much bigger than the expected value than this number, what's the chance that there are too many triangles? So to put it in a very non-mathematical way, you have this this large random graph, and there is a certain number of triangles that you expect given the model, given the number of density of edges. There's a certain number of triangles you expect, and then you ask, what's the chance that the number of triangles is much bigger than what you expect? And the second question is, what does the graph look like if such a rare event takes place? Okay. So this is an example of a nonlinear problem because number of triangles is a nonlinear function of this adjacency matrix. So the adjacency matrix is this matrix where the ijth entry is 1 if individual I is a friend of individual j, and 0 if not. So that's called the adjacency matrix. So it's an n by n matrix. And if you look at this matrix, then the number of triangles can be expressed as a nonlinear function of this adjacency matrix. Okay, it's basically the trace of the cube of this matrix. So if you think about it a little bit, you will see that it's the trace of the cube of this matrix. Okay, roughly that. You have to adjust a little bit. So the thing is, until around 10 years ago, large deviations theory didn't know how to answer such very basic questions about networks. So it's a big theory and lots of developments, since like the 1960s. But this kind of basic nonlinear questions that is, if you ask about networks, what does a graph likely to be? So just remember this earlier question that I mentioned, that if you have a sequence of coin tosses, and you look at the number of consecutive heads, and then somebody tells you the number of heads in the sequence of tosses is much bigger than what you usually expect it to be. So some rare event like that has happened. And then you can predict, just using that information, you can predict the number of pairs of consecutive heads, roughly what it's going to be, given that this rare event has happened. So that changes. So similarly here, you have this random network, and you have too many triangles. So triangle is three individuals who are all friends with each other. Okay. So suppose you have too many triangles, what would the graph look like in this situation? Given that this rare event has happened, what is the most likely structure of the graph? And we didn't know how to answer these questions, nor did we know how to compute this kind of probabilities, or approximately when n is large. So this was developed in a joint paper that I wrote with Professor Varadan in 2011, the large deviation theory for Adjacency random graphs. And this theory brought together some ideas from this classical large deviation theory and results from combinatorics and graph theory, such as Summaries Lemma and theory of graph limits. And this theory of graph limits was developed by Laszlo Lovász and co-authors. I'll talk about this also. So I'll give you an introduction to this theory of graph limits and what is Summaries regularity lemma. So again, as I said, it's going to be a little difficult, but I'll try to make it as clear as possible. And maybe some of you will take it up in the future, and so I didn't want to water it down. Just present it in its real version. Okay, so here's an example. So recall the Adjacency GNP model. So you have n individuals, any two are friends with each other with probability p. Let T be the number of triangles. Let ET be the expected number of triangles. And you look at this rare event. So let E be the rare event that T is bigger than 1 plus delta times the expectation. So delta is a positive constant. So delta may be 0.5, 0.3, something like this. So the number of triangles is, if delta is 0.5, so it says that the number of triangles is at least 1.5 times the expected value. So that's a rare event. So it's much bigger than the expected value. So the question is, what is the most likely structure of the graph if this rare event happens? So it may happen in many different ways. Are all the extra triangles containing some small subset of vertices that are highly connective among themselves? So it may be that there's a small kind of subset of vertices where the proportion of friends is much more than usual. Okay. Or is it because that the graph has an excess number of edges spread uniformly? Maybe that this happens because there are lots of people who are friends, just randomly than you would normally expect. So there are many ways this can happen. This extra number of triangles can happen in many ways. So surprisingly, this theory tells you that both scenarios can happen. More specifically, what it says is that what it implies is that there are some numbers delta 1 and delta 2, so that if this delta over here is less than delta 1 or bigger than delta 2, then conditional on this event, the graph behaves just like an Adjacency graph with some r bigger than p. So it's just as if it's just that these friendships are spread out uniformly over the graph. So there's just an excess number of friendships, and that's what gives rise to all these extra triangles. On the other hand, if delta is between delta 1 and delta 2, then the conditional structure is not Adjacency. So it's not a uniform spread. So in the middle, there is some region where you get this extra number of triangles just because there are maybe some smaller, some region which has more friendships forming than other regions. So this kind of strange behavior can happen. And these formulas, exact formulas for delta 1 and delta 2 were derived by Lubetsky and Zhao in 2014. So this is just an example of some strange things that can happen if you have this Adjacency graph, the large deviations behavior. Okay, so lessons from the previous slide is that if the number of triangles exceeds the expected value by a little bit or by a lot, then the most likely scenario is that there's an excess number of edges spread uniformly. So this nexus number of friendships spread uniformly over the graph. On the other hand, if the exceedance belongs to a middle range, then there is a clustering of edges in a small region. The exact nature of this is still not fully understood. So that's one of the open questions. We don't fully understand. We can show that it's not Erdős-Srény, but we don't know how, anything more than that. So that's, if you're looking for a mathematical open question, this is the kind of question, and you can formulate it much more precisely. But this is the question. So one thing, so this is the kind of math that you would like to do, because there is no way that these results could have been guessed. So these are deduced from these mathematical formulas, and there is no intuitive explanation. So you first do the math, and then you get the answer out of that. So there have been a lot of further developments. So this large deviation theory for the Erdős-Srény model has been extended to other more realistic models of random graphs, although not fully. So there are things that we would still like to do. So in a paper that I wrote with Percy Diaconis, this was extended to exponential random graph models. So it was extended to sparse graphs where p is going to 0. So the chance that two people are friends is not a fixed number, but is actually very small. So there, so this kind of what this is called a sparse random graph. In a paper by Amit Dembo, and this so this theory, nonlinear large divisions, is developed over here, and there have been many subsequent developments. So there are many people who have worked on this. I'm just giving a list of names, and there are many papers that are written. And again, you can see that there are some Indian or Bengali names here, and so Indians have been quite involved in this whole project. So in the remainder of this talk, I'll sketch the main steps in the theory developed here. So I'll tell you more about exactly what we are doing, instead of giving this broad overview of what's going on. Okay. And I'll also tell you a little bit about what's the theory of graph limits. Okay, so graph limit theory is a beautiful unifying theory of limits of graphs. So many of you, especially the BSc students, have seen this limits of numbers. So you have limits of numbers, and some of the master students, MSc students, may have seen this limits of functions. So you have limits of numbers, and then you have limits of functions. But what about limits of graphs? So graph, in the simplest form, just let me remind you, is that you have a set of vertices, and then many pairs of vertices are connected by edges. Okay, so that's what is a graph. And then you have larger and larger collections of graphs, and you ask, how do you describe a limit of the sequence? Okay, so there's a thing called graph limit theory that was developed between 2004 and 2010 by Laszlo Lovász, a very famous mathematician, Laszlo Lovász, and with many co-authors who are all listed here. And this is related to also the earlier works of in probability theory by Levi-Daldas, Hoover, Kaldenberg. So let me describe the basic foundation of this theory, which is a little complicated, okay, but I just want to give you the real flavor of the thing rather than just not doing justice to it. So let me try to give you the real flavor of the thing. So let Gn be a sequence of simple graphs whose number of nodes tends to infinity. Simple graphs means just what I said. Then you can have directed graphs and all kinds of other things. Simple graphs is just what I said. There is no loops and just a collection of vertices connected by edges, whose number of nodes, number of vertices tends to infinity. For every simple graph H, so H you think of as a small graph like a triangle or a quadrilateral, something like that. Let hom Hg denote the number of homomorphisms of H into G, that is H-preserving maps. So basically, if H is a triangle, you can think of hom Hg as a number of triangles in G. It's sort of like that. It's not exactly that. It's a little different, but because okay. So I'll not. So this is just a definition. The number of H-preserving maps from the vertex set of H into the vertex set of G. So VH is a vertex set of H set of vertices, and VG is the vertex set of G. And you take maps going from the vertex set of H into the vertex set of G. so that edges are preserved. If you have an edge on one side, you have an edge on the other side. So you can think of just, if this is too complex, you can think of H as just a triangle and home HG as a number of triangles in G. And then you normalize it by the maximum possible number of triangles that you can get, which is the vertex set of H, the size of the vertex set of G raised to the power of the size of the vertex set of H. So this is this is THG is a homomorphism density. So that's the probability that a random mapping is a homomorphism. Okay. So this would be something like the number of triangles in G divided by n cubed. So that's roughly, if n is the number of vertices in G. So that's called the homomorphism density. Now suppose the homomorphism density, so you have a sequence of graphs Gn, and the homomorphism density THGn tends to a limit TH for every fixed H. So it's sort of like this. So you have this large graph, you look at the number of triangles in the graph, divide by n cubed, okay? So n is the number of vertices in the graph, divide by n cubed, and you have the sequence of graphs Gn. Gn has, let's say, n nodes. So number of triangles divided by n cubed converges to a limit. Okay, but not only triangles. Now we take number of 4 cycles. So it's a sequence of 4 edges that are connected by 4 vertices that are connected by 4 edges. So it's a quadrilateral. So the number of quadrilaterals divided by n to the 4, that also has a limit. So suppose for anything that you can take on, let's say take a pentagon, number of pentagons in the graph divided by n to the 5, and all of these things tend to a limit. Tend to end limits for as n goes to infinity. Okay. So then Lovász and Szegedi proved that there is a natural limit object in the form of a function f in W, W, where W is a space of measurable functions from the unit square in 0, 1, satisfying fxy equals fyx for almost all yx. So if you don't know what is a measurable function, don't worry about that. Just think of all functions from the unit square in 0, 1, so which are symmetric. And conversely, any such function arises as a limit of an appropriate sequence of graphs. Okay, and this limit object f, this determines also the number, the subgraph densities. So you can read off this limits, this th from these using this formula. So there's a formula from which you can read it off. And then finally, a sequence of graphs Gn is said to converge to a function f if for every simple graph H you have the limit THGN equals THF. Okay, so this is okay. So sequence of graphs, the limit is described as a function on the unit square. A function from the unit square into the interval 0, 1, satisfying fxy equals fyx for all xy. Okay, that's a limit object, and then there is a criterion which says, when do you say that the sequence of graphs converge to this function f? Okay. So these elements of the script W are called graphons. So you will find this name if you search on Google graphons. There'll be lots and lots of references that you get, and people are using it for all kinds of things. So finite simple graph on n vertices can also be represented as a graph on f. Superscript G in this natural way. So what you do is you take any xy in the unit square, and then find I and j so that x lies between I minus 1 over n and I over n, and j so that y lies between j minus 1 over n and j over n. Okay. And if there's an edge connecting vertices I and j in this graph, define fxy to be 1, otherwise define fxy to be 0. Okay. So you can imagine what it's like. So you have this. You have the unit square, and you divide up into little subsquares, of side lengths 1 over n by 1 over n. So it's like a chessboard. You cut it up like a chessboard, and on each little square you put 1 or 0 according to whether the vertices I and j are connected in this graph. Okay. And then you define f arbitrarily, let's say 0 on this boundary where x is 1 or y is 1. So now this allows all simple graphs, irrespective of the number of vertices, to be represented as elements of a single abstract space. Okay, so you can embed everything in the single space of functions. So all graphs can be seen as functions. Okay, this allows you to do that. And then you want to define topology in this space. So So the MSc students will probably know what is a topology, but maybe not the BSc students. So topology would be roughly describe a distance between graphs. So how different are two graphs? Okay, so this is what you would like to understand. A distance function between graphs. So here's this thing called the cut metric. It was defined by Fries and Ravi Kannan, who is again an Indian mathematician. Defined this cut distance. So the cut distance between two functions, f and g on the unit square is defined as follows. You take the integral of fxy minus gxy dx dy on this rectangle S cross t over all subsets S and T of the interval 0, 1, and take supreme over all S and T, well, actually all measurable or else. And this is called the cut distance. Okay, so now it gets a little more complicated. So what you do is you say that two functions are equivalent if one can be obtained from the other by a measure-preserving bijection. So sigma, you know what's a bijection? So sigma, a map from set into itself as a bijection if it's 1 to 1 and onto. It's both injective and surjective. So that's a bijection. And then you have f x y equals g of sigma x sigma y for some measure preserving bijection. If you don't know what is measure preserving, don't worry about that. Some bijection sigma, then you say that f is equivalent to g. Okay. So let me give you the idea what is going on here. So two graphs, you consider them to be the same graph if one can be obtained from the other just by relabeling the edges. Okay. So if you have one graph and you have another graph, and then relabeling the vertices, and then you take the second graph, and the second graph has vertices marked 1, 2, 3 up to n, and you somehow relabel them. So 1 you make it 10, 2 you make it 5, and so on, and then you just get back this original graph. And if you get the same graph, you say that the two graphs are equivalent. Okay. So in the same way, we say that two functions are equivalent if they can be related in this manner. And then what you do is you define G tilde to be the closure in W in the space of measurable functions under this metric. So again, if you don't know topology, don't worry about this. So of this orbit. So you look at all functions that can be obtained in this manner, starting with some G. You look at all functions that can be obtained in this manner with measure-preserving bijections. And you take this whole class of functions, and then you take its closure under this metric, okay, if you know what that means. And that you call G tilde, okay? So that's sort of like an equivalence class. And this quotient space, W tilde, under this mapping G to G tilde, so you take each of these equivalence classes, okay? So instead of individual functions, you look at equivalence classes, okay, of functions. So you take a function and then you look at all its possible transformations with this prescription, and this is called W tilde. So this is the space of graphons, and on this you can define a distance as the following: delta box, this cut metric of f tilde and G tilde, is the minimum of f sigma 1 and G sigma 2 over all sigma 1 and sigma 2. So you basically what you do is you have these two graphs, and you want to define a distance between two graphs. So the first thing, this cut metric over here of Fries and Kannan, what it does is that it just takes these two graphs and it measures in some way how different they are. But then here what you're doing is that you're looking at all possible relabelings of vertices and how close you can make the two graphs after relabeling vertices, and the closest you can make, and then you take the distance between them. So that's the distance on the quotient space. Okay. So this is called the space of graphons. So this is one of the main results in this theory of graph limits, is that for any finite graph G, we can associate a natural graphon and its orbit, which we call G tilde, in this quotient space. And one of the key results is that a sequence of graphs converges to a limit function f if and only if this cut distance between the images G and tilde and f tilde goes to 0 as n goes to infinity. Okay, so this cut metric kind of captures this notion of graph limits that I mentioned earlier. Okay, so this is roughly, the theory of graph limits, the language that we talk about graphs and their limits nowadays. So this is important thing to know. And if you want to know more, you can check out this book from the library. Las Lovas has a big, thick book on graph limits that he published sometime in 2012. So it's a flourishing area. Okay, so here is the large deviation principle for heterogeneous random graphs. And the reason I introduced this whole theory of graph limits is because I needed that language to tell you this result. So the random graph GNP that I introduced before, so you have n vertices and edges are present with probability p and absent with probability 1 minus p. This induces a probability distribution on the space of graphons through the map G going to G tilde. So you have this random graph. So any graph, remember, any graph has an associated graphon. Okay? So this random graph induces a random graphon, and that random graphon induces a probability distribution on the space of graphons. Define this function, IP of u is a number between 0 and 1, as half u log u over p plus half 1 minus u log 1 minus u over 1 minus p. And then for any graphon H, you define IP of H tilde. H tilde is the equivalence class. So this is invariant. This double integral is invariant under equivalences. So you define IP of H as double integral IP HXY dx dy over the interval 0, 1 cross 0, 1. And this is what we showed. We showed that for any closed set F tilde contained in W tilde, the lim sup of 1 over n squared log of this probability. So this means that probability that the random graphon GNP belongs to F tilde is bounded by this minus this infimum. And for any open set, you have the opposite thing. Lim inf of the probability 1 over n squared log of this probability is bigger than minus the infimum of this IP of H tilde. So again, this may seem completely opaque to when you look at this, but you can deduce very concrete actual numbers actually from these computations. So often what happens is that you take any set, it can be sandwiched between a closed set and an open set where the infima are the same, and you can actually obtain this these limits, calculate the limit of 1 over n squared log of this, and then you can conclude various things like what's the chance the number of triangles in the graph is at least something. So what is the limit of that? And that kind of thing you can compute from this general formula that I just wrote down over here. Okay, but writing down this formula took us through this graph limit language. Otherwise you cannot really write down the formula over here. So let me tell you a little bit about the proof in case you are following until now. Okay. So the large deviation principle can be proved by standard techniques for the weak topology. So there are some standard methods in large deviation theory. However, the weak topology is not very interesting. So we are working in this cut metric, which is a different topology, different way of measuring the distance. And this does not follow from these standard methods. So we need some new methods. So that's what we did. We developed these new methods, which weren't there in the theory of large deviations before. So here is something that if you have not followed anything until now, here is something that's an extremely important thing. It's called Summaries Lemma. It's one of the foundational things of graph theory. And it's a very deep thing that it is good to know. So let G equals V comma E be a simple graph of order n, which means that V is a set of vertices, E is a set of edges, and number of vertices is n. And simple means that there are no self loops or multi edges and all that. So just a simple graph. Okay. So for any two subsets of vertices x and y, let EXY be the number of xy edges of G. So number of edges between x and y. Okay. And rho xy be this EXY divided by the size of x times the size of y. Okay. So the size of x times the size of y, if x and y are disjoint sets, this is the maximum possible number of edges that you can have between x and y. So you take the actual number of edges, divide by the maximum possible number of edges. This is called the edge density between x and y. And you say that a pair of disjoint subsets of vertices are epsilon regular if for every x contained in A and y contained in P, where the size of x, so x with 2 bars, it means the size of x, is at least epsilon times the size of A, and the size of Y is at least epsilon times the size of B. So these sets are not too small. Okay, so this epsilon is some fixed number. These sets are not too small, x and y, satisfy that the edge density between x and y is within epsilon of the edge density between A and B. So this is called an epsilon regular pair of disjoint sets of vertices. Okay. So what is the edge density? It means you have two sets of vertices. You have some edges going between them. So let's say, one vertex set has 100 vertices, another has 200 vertices. So the maximum possible number of edges between these two sets would be 200 times 100, which is 20,000. Okay, 20,000 edges. But suppose actually the actual number of edges that are present is 10,000. So the edge density is 0.5. 10,000 divided by 20,000. So not all edges are present. About 50% edges are present. Okay. So you say that AB is epsilon regular if not only so you take this 100 and 200 vertices on two sides, and there are among 20,000 possible edges, only 10,000 are present. So it's called epsilon regular if you take any two smaller subsets. So let's say a subset of size 10 and a subset of size 20. So there are 200 possible edges between these two sets, 10 times 20. And even in the small subsets, you would see approximately half is present. So about 100 edges are present instead of 200. Okay. So the edges are kind of uniformly spread out. So this is called the epsilon regular pair. A partition of V0 up to Vk. So partition meaning that disjoint sets whose union is V. It's called an epsilon regular partition if it satisfies the following conditions. There is one set V0 which is kind of small, less than epsilon n. All the others have equal size. And all but at most epsilon k squared of the pairs are epsilon regular. Okay. So most pairs are epsilon regular. So between most pairs, the edges are sort of uniformly distributed. The Summaries Lemma tells you that given any epsilon and any m, there is a number big M depending only on epsilon and little m, not depending on the graph at all. Okay, such that for every graph of order big M or larger admits an epsilon regular partition for some k between little m and big M. So I'll tell you roughly what this means. It means that given any large graph, you take any large graph, and let's say it's a dense graph, which means that the number of so if the graph is of size n and the number of edges is of order n squared, then it's a dense graph. Okay. So you have this large graph. Any large graph can be partitioned into subgraphs of equal sizes, so that between most pairs of the subgraphs, the edges are uniformly thrown about, uniformly distributed. So it's an extremely important structural thing, and it's true for all graphs, and it's a deep result, Summaries Lemma. So how do we use Summaries Lemma? So this would be sort of this second last slide. The last slide will have some open questions. So suppose G is a graph of order n with an epsilon regular partition V0 to Vk. Let G prime be the random graph with independent edges where a vertex U in Vi and is connected to vertex V in Vj with probability rho of Vi Vj. So you take your original graph and you look at this epsilon regular partition, and then you define a random graph which just does the following. Between any Vi and Vj, you throw the edges independently and you at random with probability rho Vi Vj. So it's sort of mimicking this graph G. Using Summaries regularity lemma, one can prove that the cut distance between G and G prime is close to 0 with high probability if K and N are appropriately large and epsilon small. And let F be the probability density of the law of G and P with respect to the law of G prime. So again, don't worry if you. So this is just for those who are still following, who have some deeper knowledge of probability. Let F be the probability density of the law of G and P with respect to the law of G prime. So this can be easily computed. This gives rise to the entropy function. And then the chance that your graph GNP, the random graph, is close to this graph G, this fixed graph G, would roughly be f of G times the probability G prime approximately equal to G. And this approximately equals meaning that in this cut metric sense. And this probability is close to 1, so this you get FG. So then what you do is this space W tilde is compact. This I didn't state, but this is one of the other main results of graph limit theory, that the space W tilde is compact. So then you can, if you have a compact space, again, for those who know a little bit of topology, you can break it up into a finite number of small balls. Okay, that's the basic property of compact sets. And then you can write down the probability GNP is in any set A by approximating A as a finite union of small balls. So this is in a brief, broad of the argument, and don't worry if you didn't follow that. So the question is, what do you do next if you want to do research in this area? So theory has been in development for almost 10 years, and the main questions have more or less all been solved. However, there is one very big unsolved question. There is still no good theory of graph limits for sparse graphs. So what I said is, for dense graphs, there is this graph limit theory developed by Lofaz and others, and this is a huge development. But there is no good theory of graph limits for sparse graphs. And as a result, the large deviation results that we have for sparse graphs, which I didn't state here, only gives estimates for probabilities. We do not know how to talk about this graphs with this conditional behavior. So suppose some rare event has happened. What is the structure of the graph? So we don't have language. We don't have the language even to express this. So we don't know how to say what does it look like. Okay. So it would be a great contribution if one can make progress on this front. Okay. So that is all, and thanks for listening. And and as I said, in the questions, I'll be very happy to answer any questions you have, and you can ask them in Bangla if you are more comfortable in that, and that is all fine. Okay, so thank you.
Thanks, Professor Sourav Chatterjee, for such an excellent speech. But it seems like some of the participants want to ask you some questions.
Okay.
I would request our participant them to ask their questions one by one.
বাংলাতেও কোশ্চেন করতে পারো, স্যার তো ফ্রিডম দিয়েছে, বাংলাতে বলো, তাছাড়া আরো হ্যাপি হবে বাংলা করতে।
বলছে
এই ব্যাপারে কোনো রেফারেন্স পাওয়া যাবে?
Reference ache. So I'll answer in English because there may be students who don't understand Bengali. So the references are mostly in papers. So I have a book called Large Deviations for Random Graphs, which you can look at. So that's a Springer monograph. But there are more developments after that. So the book was written in 2015, but there have been many more developments after that. And there's one other reference. So I also have a survey paper in the Bulletin of the American Math Society, Bulletin of AMS একটা survey আছে। সেইখানে মানে জেনারেল একটা ওভারভিউ দেওয়া হয়েছে এবং রেফারেন্সেস জেনারেল, but it's mostly all in papers because it's still a theory in development, and it's not been very long, so it's all mostly in all the papers. So one first thing you can do is you can look at my original paper with Professor Faradan. That you can do, and you will get all. So you'll get the links from my homepage. So if you type in my name in Google, you'll see my homepage, and there you have my list of publications, and you can go in that and look at this paper with Professor Vardhan, and that's the first paper, and you can read about that. So that's a good starting point. And if you want to look at something more recent, which gives you everything that has been done, well, one thing is to look at my my survey. That is also on my homepage. So it's called this Introduction to to Large Deviations for Random Graphs. That was the survey that appeared in the Bulletin of AMS. So that is one place where you will get a broad overview of the things. And if you want to look at more recent developments, then it's best to look at. Okay, so if you get up to that point, you can write me an email, and I'll send you the references. So if you are comfortable with all the previous the early things that have been done, and then you have reached a point where you want to start thinking about some research questions, then I'll be happy to answer your questions. Yes, sir.
Thank you, sir.
I have one question.
Hmm.
Can you visualize card distance or card metric in figure diagram?
Yes, it's a little difficult because these are distances between graphs. So these are not distances between points. And also I don't have a blackboard to write, so it's a little hard. So what you do is okay. Let me try to explain in terms of graphs. So not going to functions. So what's the cut distance between graphs? So that was the original definition of Fries and Canaan. So what's the cut distance between two graphs? So what you do is the following. So you have two graphs defined, let's say, on the same set of vertices. So the set of vertices is 1 up to n for both graphs, and then you have two different graphs. So then you look at any subset, any two subsets of vertices, let's say A and B are two subsets of vertices. You look at the number of edges between A and B. Okay. In one graph, you look at the number of edges between A and B in the other graph. You take the difference between these two numbers, take their absolute value, and then you take maximum of all possible choices of A and B. Okay, so that's the cut distance. So if two graphs are the same, then this is obviously 0 because again two vertices, any two sets of vertices A and B, the number of edges between A and B is the same in both graphs because both graphs are the same. So this difference is 0. You take the supremum, that is 0. On the other hand, if this cut distance is 0, then you can say that the two graphs are the same because for choices of A and B, you take A and B to be singleton sets, so just a single vertex I, that is A, and single vertex J, that is B. And then if the cut distance is 0, then it just says that there is an edge between I and J in one graph, if and only if there is an edge between I and J in the other graph. And so then you say the two graphs are the same. But in general, this is one way of measuring the distance between graphs. That is, you take all possible choices of A and B, look at number of edges between A and B. And it's actually a very important question, and it's sort of an open question. How do you compute the cut distance in a reasonable amount of time on a computer? And that's not so clear. It's a complicated distance, and it's very time-consuming to compute. There are some algorithms, I think, but it would be nice to be able to compute it quickly on the computer.
And open ball card metric.
What? I didn't get the question.
And then we did that. Okay.
An open ball in the cut metric. So an open ball would be the following. Yeah, that's a very good question. When are two graphs close in the cut metric? Yeah, so it's not so easy to answer when are two. Okay, so roughly what this. So suppose two graphs are close in the cut metric when normalized by n squared. So you take what I just told you and divide by n squared. That's the normalized cut metric. That's what we're using. Suppose that is small. So what that would tell you is that if you take any two sets A and B, which are kind of large, macroscopic. So the size of A and size of B are comparable to the size of the graph. So that's the kind of set, A and B, not too small. You take any two sort of large sets, A and B, the number of edges between A and B divided by n squared is close to the number of edges between A and B divided by n squared in both graphs. Okay, so the microscopic structure may differ. So if you look at small regions, then the number of edges between them may be quite different in the two graphs. But if you take sort of large regions, then the number of edges going from one to the other is approximately the same as the number of edges going from one to the other in the other graph. So the macroscopic structure is the same, but the microscopic structure may differ. So that's what the cut metric is trying to capture. It's a difficult question. Yeah. Okay. Right. So the thing about the cut metric is that, okay, let me tell you a little bit more about the cut metric. So there are three kinds of things that you can consider about these metrics on these functions, function spaces. So you can have the strong topology, which is the L1 metric, and you can have the weak topology, which is the weak convergence, L2 weak convergence that you can have. Cut metrics lies somewhere in between. So what you want really is that these functions, these triangles, number of triangles, number of quadrilaterals, this kind of thing, you want those to be continuous with respect to the topology you're working in, because you want to deal with those things. But at the same time, you don't want the topology to be so strong that you lose the compactness. Okay. So the weak topology, this is for those of you who know some functional analysis. The weak topology is compact. Okay, or at least the L1 ball in the weak topology, the unit ball in the weak topology is compact by Banach-Alaoglu theorem. So the weak topology is compact, but the weak topology is too weak to do any useful math. On the other hand, the strong topology is a good topology. You can do math with that, but strong topology is not compact, which is a big problem. Okay, you cannot do much with the strong topology because it's not compact. So the cut topology, the topology induced by the cut metric lies somewhere in between the strong topology and the weak topology. It's in between, which has a rich enough collection of continuous functions to allow you to do the math, but at the same time is weak enough to have compactness. Okay, that's the main thing about the cut topology. And that was the main realization of the graph limit people, that they, particularly of us, that this is the right thing to work in.
ওদের কোশ্চেন থাকলে বলো স্যারকে, প্লিজ টেল এনি কোশ্চেন।
হ্যালো স্যার, কম্বিনেটরিক সম্পর্কে কিছু শর্টে বলেন, কম্বিনেটরিক সম্পর্কে।
কম্বিনেটরিক্স তো মানে স্পেসিফিক্যালি কিছু জানতে চাইছো না? মানে অ্যাজ এ সাবজেক্ট কম্বিনেটরিক্স এর ব্যাপারে জানতে চাইছো?
হ্যাঁ স্যার।
So combinatorics, is a flourishing field. There's lots of actually deep work that is going on in combinatorics. So combinatorialists look at all kinds of things. Graphs are one. Graph theory sort of is one part of combinatorics, and it also has this intersection with probability theory. And so this work that I just described lies at the intersection of probability and combinatorics. So there is some probability and there is some combinatorics. This graph limit theory is part of the combinatorics literature. Lovas and other people who worked on that are many people from combinatorics. So the older combinatorics that you probably learn in college is about just counting things. Okay. It's still about that, but there has been huge developments, and it has become a very rich area, very deep and rich area that lots of people work on. And And it's a good area for doing research if you want to do research in math in the future. You can do combinatorics, and there are many good places where you can do research in combinatorics. So again, if you're interested at any point, you can write me an email. I'll try to guide you about that if you want to do research in combinatorics.
Thank you, sir.
Sir, can you share a lecture presentation?
Like the slides?
Yeah.
Yeah, sure. I can send the slides. That's fine.
So this lecture is very important, and I also this lecture, that is card matrix in the field of algebraic topology, graph theory, action, orbit space. Important for my research work.
Okay. I'll be glad to do that. In fact, I'll be glad to share it with anybody, and Yeah, no, I was a little worried that it may be a little too complex for the students particularly, but if some of you can benefit from this, I'll be very glad.
I think many are shy to not ask question. Actually, sir has also his email ID is there. In future, if you think or feel anything, you can write to sir. I think sir is glad to satisfy your query. So today I actually request for such a very interesting and very lucid way, such a very challenging field of this type of probability theory and its mathematical this computation. He actually such a lucid way present everything, and such a memorable lecture he has given. So I request our Dr. Prabhanjan Kumar Rana, the head of the department, to actually give this thanks, propose the vote of thanks of this beautiful session.
I am very much thankful to our principal for continuous support and advices, which has greatly helped towards the success and fruitfulness of this program. Again, I would thank Professor Sourav Chatterjee, who took the time out of his busy schedules and showered us with his pearls of wisdom and knowledge. We truly humbled by his presence. Thanking you once again. I am thankful to all the participants to remain in this program from the beginning to the end and motivate us with their gusto and enthusiasm. I am pretty sure that the participants are benefited by attending this program. Thank you so much for being our pillars of support. Thank you.
সৌরভ বাবু, খুব ভালো সেশন এটা হলো। এবার আমাকে আগেও বলেছি কলকাতায় এলে ছাত্রদের এখানে আসতে হবে, একবার আমাদের ইনস্টিটিউটটা ভিজিট করতে হবে, এই আর কি।
নিশ্চয়ই। কেউ যদি স্লাইড গুলো চায় আপনাকে আমি পাঠিয়ে দেবো, তাহলে আপনি কেউ যদি চায়
পাঠিয়ে দিলে আমি ওই সব স্যার চাইছিলেন, আর অন্য ছেলেরা লজ্জা পাচ্ছে, মানে চাইবে কি চাইবে না এরকম। আপনি স্যার আমি ওটা আমি দিয়ে দেবো, কারণ ওরা এত লুসিডলি হয়েছে সেটা তো সবাই বুঝতে পারছে। আপনি সিম্পল ভাবে কত নেমে জিনিসটাকে একটা এরকম টাফ থিওরিকে এইভাবে বুঝিয়েছেন, মানে রিয়েলি এটা আপনার জিনিয়াসনেস এটা। আদারওয়াইজ এইরকম খুবই টাফ থিওরি একটা, সেটাকে এই জায়গায় আপনি এক্সপ্লেন করছেন এটা।
না, মানে আমার তো ব্যাড লাগছে, এটা জুমে করতে হচ্ছে, আর এক্সপ্লেন ঠিক করে করতে পারছি না। ব্ল্যাকবোর্ডে করতে পারলে খুব ভালো হতো আর কি, সেটাই।
ঠিক এটা তো